This video program shows the components, functions, and the testing and adjustment procedures for the K-Jetronic. What actually is the K-Jetronic? K stands for continuous. Jetronic is the description given by Mrs. Bosch to fuel injection systems. Let's first consider the parts which make up the K-Jetronic and consider how they function. First, the fuel supply system. In order to show this more clearly, the pump assembly has been removed. It consists of a fuel pump, fuel pressure accumulator, and filter. The fuel pump draws the fuel from the tank through the fuel pipe and pumps it into the pressure accumulator. This pressure accumulator mutes the delivery pump noise and maintains a specific pressure in the system after the ignition has been switched off. This inhibits the formation of vapor bubbles and facilitates trouble-free hot starting. Fuel is directed from the pressure accumulator to the fuel filter. From there, the fuel is directed to the fuel distributor in the mixture control unit. At the mixture control unit, we differentiate between the airflow sensor and the fuel distributor. The fuel distributor has the task of providing a correctly measured amount of fuel relative to the inducted volume of air and of distributing this amongst the individual cylinders. The fuel distributor consists of the following parts: the upper and lower housing sections, the steel membrane which simultaneously separates and seals the two housing sections, the metering slit barrel with control plunger, the differential pressure valves, the primary pressure control and non-return valve. The warm-up regulator. Its job is to adapt the composition of the mixture according to the engine temperature and load. How is this achieved? When the engine is cold, a bimetal strip causes a lowering of the control pressure. In this way, it's possible, with the same quantity of air, for the sensor plate and control plunger to travel upwards further, allowing more fuel to flow through a consequently greater open section of the metering barrel slits to the injection valves. When the engine is warm, the bimetal strip function is inoperative. The control pressure is thus increased. A higher control pressure means less fuel. Quite independently of these temperature-related factors, The respective control pressure is additionally corrected through the vacuum pressure in the suction pipe via a membrane in the warm-up regulator. This means that high vacuum in the intake system results in higher control pressure, i.e. less fuel. Lower vacuum produces lower control pressure, i.e. more fuel flow. Dependent upon installation position, the warm-up regulator is mounted upon a heat retainer. This prevents the bimetal strip from cooling too quickly after the engine has been switched off. Now the auxiliary air device. It allows more air to be drawn in by the engine in the cold state, bypassing the throttle valve. In this way, the friction losses, which are greater when the engine is cold, are compensated for. Idle speed is increased. There are two models of auxiliary air device available. One, which is electrically, and the other coolant controlled. Now for the cold start facility. This is a starting aid for cold conditions. It consists of the thermotime switch, the 0-degree switch, the cold start relay, and the cold start valve. When the engine is started, dependent upon actual temperature, additional fuel is sprayed by the cold start valve into the intake manifold. The duration of this additional fuel injection is dependent upon the setting of the thermotime switch and the duration of starter motor engagement. At a temperature of -20 degrees centigrade, the thermotime switch supplies the cold start relay with earth for a period of 12 seconds. At a temperature of 35 degrees centigrade and above, there's no additional injection. To improve cold starting, a 0-degree centigrade switch has been incorporated into the cold start facility. This has the effect of holding the cold start relay operative at temperatures below 0 degrees centigrade. Thus, the duration of the additional injection is dependent solely upon the function of the thermotime switch. Those were the various parts and their functions. Let's look at them again in sequence. We've been discussing the fuel pump, the fuel accumulator, the fuel filter, the mixture control unit, which consists of the airflow sensor, and the fuel distributor. The primary pressure regulating valve, the warm-up regulator, the auxiliary air device, and the cold start facility, which consists of the thermotime switch, the cold start relay, the cold start valve, and the 0-degree switch. Now for test and inspection procedures. Before starting work on the K-Jetronic, make absolutely sure that the engine is running well. Ignition and valves must be properly set, and the spark plugs must be functioning effectively. Exactly how the work is carried out on the system will now be demonstrated by our technician. Let's start with the fuel system. First, a visual inspection. We check all hoses and supply line connections for seal. Then we check the fuel flow quantity. We want to know if enough fuel is being supplied to the mixture control unit. The tools required for this task are this petrol pipe and a measuring container of about 2 litres capacity. The pipe is attached to the return line of the fuel distributor. In order to bring the fuel pump into operation when switching on the ignition, detach the fuel pump relay and bridge terminal 15 to terminal 87 at the relay socket. Caution: if terminal 15 is mistakenly bridged to terminal 31B, the control unit of the ignition circuit will be shorted out. The electrical connections to the warm-up regulator and the thermotime switch are also detached. Should the engine have an electrically controlled auxiliary air device, this connection here is removed as well, to prevent the heating elements from warming up unchecked. Switch on the ignition now for a period of 30 seconds. A minimum of 750 cc of fuel must now be in the container. If there is less than 750 cc of fuel in the container, the reasons for this could be the following. The fine filter in the tank unit is clogged. The fuel feed pipe has a kink. The fuel pump has a faulty electrical contact or is worn. The fuel filter is clogged. If it is to be exchanged, note the fitting instructions on the filter housing. Now checking pressure. We check both the primary pressure and the control pressure. The primary pressure is provided by the electric fuel pump and controlled by the primary pressure control valve in the fuel distributor. The fuel for the control pressure circuit is tapped from the primary pressure circuit. The actual pressure is determined by the warm-up regulator. The control pressure, formed above the control plunger, constitutes the opposing force to the air pressure acting on the sensor plate, which, in relation to the sensor plate's position, determines the actual composition of the mixture. To check the primary pressure, we unscrew the pressure pipe leading from the fuel distributor to the warm-up regulator. The tools required are this and this testing connection. And the 10-bar pressure sensor. One end is screwed to the fuel distributor. The other to the control pressure pipe of the warm-up regulator. We clamp off the pipe to the warm-up regulator and switch on the ignition. The tester should show a primary pressure value of between 4.5 to 5.2 bar. The tester should show a primary pressure value of between 4.5 to 5.2 bar. Should the primary pressure reading not be between these limits, it can be adjusted up or down by adding to or removing these washers in the primary pressure valve. The actual control pressure valve is dependent upon temperature. We therefore measure the temperature of the warm-up regulator. We do this using the service tester temperature probe. Now we can test. We open the clamp and switch on the ignition. The pressure indicated must correspond to the value as shown in the table for the temperature as just measured at the warm-up regulator. If the control pressure is not within the given tolerance, it could be due to the following. If the control pressure is not within the given tolerance, it could be due to the following. The return pipe is kinked or incorrectly routed. The non-return valve in the fuel distributor could be defective. Or the warm-up regulator is defective. We remove the return pipe from the warm-up regulator at the fuel distributor, plug the opening, and again test the pressure. If the pressure reading is still outside the tolerance limits, then the warm-up regulator is defective and must be exchanged. If it is not defective, we check the non-return valve in the fuel distributor, then the return pipe for blockage. The auxiliary air device check. We differentiate here between the coolant-controlled and the electrically controlled auxiliary air device. In order to check the openings, we remove the auxiliary air device. In the electrical version, the air bore is approximately half open when the engine is cold, i.e. at about 20 degrees centigrade. The coolant-controlled auxiliary air device must show a gap of 5.5 millimeters at 20 degrees centigrade. Setting corrections can be made via the adjusting screw of the expansion element. After remounting the unit, the pipes are reconnected and the engine started. When the engine is cold, then if the air supply is interrupted by clamping the hose off, the engine revolutions must drop. Should the engine be warm, then there should hardly be a noticeable difference when the hose is clamped off. If this is not the case, now to inspect the mixture control unit. In order to check that the sensor plate is correctly positioned, we've removed the air intake dome at the airflow sensor. Correctly positioned, the upper edge of the sensor plate is flush with the base of the air funnel. It must not be seated higher than the funnel base or maximum 0.5 millimeters below. The zero position can, if required, be adjusted by bending this leaf spring. After checking the sensor plate positioning, we check the airflow sensor fulcrum for ease of travel. Switch the ignition on for about 5 seconds. After switching off, a residual pressure will have been maintained, causing the control plunger to come to rest on the fulcrum. If the sensor plate is now moved upwards, an even resistance must be felt during the whole length of travel. If the sensor plate is then allowed to fall back downwards again, it should show a spring-like return to the zero position. Let's pull the sensor plate upwards again, then return it slowly to the zero position. One should be able to feel the constant contact of the control plunger. If the fulcrum movement becomes impaired, the airflow sensor must be exchanged. If control plunger movement is impaired, the fuel distributor must be exchanged. Checking for seal is the last test of this system as a whole. To do this, we switch the warm engine off. After a standing period of 20 minutes, the residual pressure in the system should register a minimum of 1.5 bar. Should this not be the case, then the non-return valve of the fuel pump, the pressure accumulator membrane, the non-return valve in the fuel distributor, the cold start, and the injection valves must all be checked for seal.